So let's get one that looks like it might be a matrix transformation, but is not. So not a matrix transformation. Not a matrix transformation. And here it is. I have y1 equal to negative 4x1 plus x2. y2 is equal to 2x1 plus 7. Now, if you look at this one, it looks very similar to the first one we did. And it feels like it should be a matrix transformation, but why is it not a matrix transformation? Remember I said a matrix transformation can be written as A times V and only as A times V, nothing else added. So when I look at this one, right, I can do this the same way we did the other one. I have T, I have X1 and X2 are my only inputs. So I have T of X1, X2, okay, equal to, I'm going to have my matrix times my inputs, X1, X2. Right? If this is a matrix equation, it should be T of X1 is equal to some matrix times X1, X2. So what goes inside my coefficient matrix? Well, I have here what? Negative 4, 1, 2, and it's not going to be 7. It's going to be 0. Where does the 7 go? The 7 has to be tacked onto the outside. So it'll be like this, 0, 7. So this is not a matrix equation because essentially I have this instead. I have A, V plus B. Okay? I have A times V plus B. This is not a matrix equation. Or not a matrix transformation. Sorry. This is not a matrix transformation. Because the only thing it should be is A times V. And this is the issue because of this guy right here. Now, usually I talk about a lot of other things, but let's just kind of wrap it up a little bit early. We're going to talk about just kernel and range of a matrix transformation, and we're going to stop there. We're going to talk about kernel and range of a matrix transformation. So let's talk about what a kernel is. So definition, kernel and range. So definition, kernel and range. So that's what we want to talk about. I can talk about the kernel range of a linear transformation altogether, and that's what we're going to talk. We're going to give the definition of a kernel and range for a linear transformation, but then we're only going to do it for a matrix transformation, just for the sake of time and my sanity. Let's do it. Definition. Let T be a transformation from B to W. The set of all vectors B in capital V, my vector space, my Euclidean space, that satisfy that T of V is equal to the 0 vector is called the kernel of T. kernel of T. Kernel of T. Denoted, I'm going to erase this. Denoted, K-E-R in parentheses T. Ker-T. I had a girlfriend that called me Ker-T. Don't ever call me Ker-T. Okay. So essentially, it's the x-intercepts. Just like we did with the null space, it's essentially the x-intercept. The kernel of T is the x-intercepts of the transformation. So the kernel is the x-intercepts. And I'm going to put that in quotes of the transformation. We talked about this before, right? Where essentially when you plug in that value, that vector, you get the zero vector. You get essentially where it lies along the x-axis. Although in this case, it's where it lies along the zero vector, right? It lies on this kind of this zero plane that we're looking at here. So the kernel is the x-intercepts of the linear transformation. Okay. So essentially all values, all vectors that are going to go to the zero vector. That's the kernel. And then the range of T is the set of all vectors T of V in W, denoted range of T. And we talked about this before, right? The range of T is going to be essentially all the outputs that your function gives us. You guys have dealt with this all the time in any class, right? If I have f of x is equal to sine of x, okay? The range of f is between -1 and 1, right? It's not going to be all real numbers. That's not the range of f. The range of f for this particular function is from -1 to 1. Its codomain is R, right? The codomain of this function is all real numbers, but its actual range inside of that codomain is just from -1 to 1. So that's what we mean by, essentially what we want to do is we want to find the range of the linear transformation. Okay. The range of the linear transformation. So the kernel of T is a subspace in V. Okay? The kernel of T is a subspace in V. The range of T is a subspace in W. So the kernel of T is a subspace in V. The range of T is a subspace in W. Again, let me kind of illustrate this. So here, suppose that this is the kernel of T. Okay. Okay. All the values in the kernel of T, will go to the zero vector in W. Okay. V in W. All right. All right, so almost done. We're not going to talk about all of these guys. Let's just talk about matrix transformations. It's very easy to find the kernel range of a matrix transformation. We're going to put it down. Okay. The kernel of a matrix transformation is the null space of A. Okay. Is the null space of A. The range of a matrix transformation is the column space of A. It's the column space of A. So the kernel of a matrix transformation is the null space of A, which makes perfect sense because I told you the null space is also the x-intercepts of my essentially A times X, or my A times V matrix equation. So when we saw the kernel of a matrix transformation being the null space is perfectly understandable because a matrix transformation is A times V, right? Or A times X, whatever you want to call your vector. And the range of a matrix transformation is the column space of A. Okay. So, all thing we have to do is find the range. To find the range of the kernel is to find the column space and to find the kernel. To find the kernel, we just need to find the null space of A, and to find the range, we just need to find the column space of A, right? And so let's do that. Let's do an example. Let's do an example here. Bear with me while I find my example. Well, let me just make one. Now, when Dr. Wesley makes up a problem, there's always some issues there, but I'll try to keep it simple. X, Y equal, I have X minus Y, and then I have here X plus Y. Minus X plus Y, let's do that. So I have X minus Y, I have minus X plus Y. So I kept it pretty simple. Find the kernel and range. Okay, find the kernel and range. So let's look at that real quick. Woo! The first thing I need to do, I know that this is a matrix. I know that this is a matrix transformation. You might not see that as a matrix transformation, but I see it automatically. This is a matrix transformation. So let's write this. Let's write this as a matrix transformation first. So I have T of XY is equal to, in this case I have 1, negative 1, negative 1, 1, X times Y. I need a new marker because this one's dead. Okay. Now, here is my matrix A. Okay. I need to find the column space and the null space, right? So let's do that. Let's find the null space first. Kernel T. Getting used to the smaller board here. find the kernel of T. Right, so that means I need to find the null space of A. Okay. To find the null space of A, right, I have my augmented matrix. You guys just had a test over it, right? Or will you have a test over it soon? I don't know. I'm in the future here for you guys. Where this lands, I'm not quite sure just yet. Might be almost a second to the last. It might be inside of exam number 3, or it might be outside of exam number 3. But definitely inside of the purview of the final, right? So we have 1, -1, -1, 1, and then I have my dashes. Zero, 0. Okay. Again, what I said before, you don't have to add the 0 zeros, but I like to add them just to remind myself that I'm dealing with the null space. Then I take the reduced row echelon form of this. Get 1, -1, 0, 0, 0, 0. Zeros everywhere. So my system, okay, when I do this, my system is going to be, let's call it x minus y is equal to 0. So my solution is that x is equal to t, y is equal to t, right? And so my vector is going to be 1, 1 times t. Okay. So my null space, if we look at it like this, my null space of A is going to be the span of the single vector 1, 1. Essentially, I'm dealing with a line in R2, right? Given this direction by giving the direction 1, 1. Or I can think of any linear combination of the vector 1, 1. When I plug it into my transformation, it will always give me 0, 0, right? So any combination, so any linear combination, so it's essentially any scalar multiple because I only have one vector here. So take 5, 5, 7, 7, 8, 8, 100, 100. If I plug it in there for x and y, right, I always get 0, 0, right? I get the 0 vector back. So my kernel of T is the span of 1, 1, right? Because the kernel of T is the null space of A. Okay, let's do the range of T. The range of T is going to be the column space of A. Column space of A. And so essentially I need to find the reduced row echelon form of A transpose, right? Well, the reduced row echelon form of A transpose is actually going to be 1, -1, 0, 0. And then I take my row, take the row, my only non-zero row, so my column space of A is equal to the span of 1, -1. So my range of T is going to be all multiples of 1, -1. And you can try it out for yourself. Take any x and any y value that you want, right? Pick any x and any y value that you want. And you'll see that your answer is going to be a multiple of 1, -1, right? All of your outputs are going to be multiples of 1, -1. Okay. let's do one more example. So that's the range of t. Let's do one more example. Just a really, really easy, really, really straightforward example. Very, very straightforward. Suppose I have t of x, y, z is equal to, here I have 2, 0, 0, 0, 3, 0, 0, 0, 4, x, y, z. I want to find the kernel range of t. Oh, by the way, the range of t is also going to be a line in R2, right? For my previous example. Okay, so this one's a really straightforward, simple example. I want to find a kernel and a range of t, right? I've already broken it up so that you can see that this is a matrix equation, right? You don't have to do any work at all to put it into the matrix. I keep saying matrix equation. I already put it into the matrix transformation form, so you didn't have to do any work at all to put it into that form. But I still need to be able to find a kernel and a range of t. So what's kernel t is going to be the null space of A. So let's start with that one first. Okay. And here, when we do this one, I'm going to have 2, 0, 0, 0, 3, 0, 0, 0, 4, 0, 0, 0. I have a augmented matrix form here. Dot, 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 dot. Reduce row echelon form in this one. You guys can probably see it. Just divide the first row by 2, the second row by 3, the fourth row by 4. Reduced row echelon form is 1, 0, 0, 0, 1, 0, 0, 0, 1, dot, 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 0, 0, 0. My system is